Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to integral calculus students who are currently going through trig integrals, which is not the same as trigonometric substitutions. Prior to this, you should be very familiar with integration in general, just what it is. You should have already gone through U substitutions and integration by parts. Those are the only things you really need to know as far as your Calc 2 content before watching this video. The purpose of this video specifically is just to go through a single example of how you would integrate something like this. So we're evaluating the indefinite integral x tangent squared of x dx. Now this problem could be in a by parts section, or it could be in a U substitution section as long as you've learned integration by parts already. But just to give you a heads up, you don't want to always think about, oh, what section am I in? Then I should use the methods taught in that section, because that's not going to prepare you well for integration within calculus. You want to keep your mind open to all the possible techniques that you have at your disposal at the time and consider each one of them in turn. So in this case, I know that's a product of two functions. Well, maybe I should step back and just write this out. Can we do direct integration? In other words, do I know the antiderivative of this offhand? No. That one is almost always a big fat no when you're in Calc 2. You don't know the antiderivative offhand. The next integration technique that you learned was U substitution, or some people call it the substitution rule. That's fine, whatever. But looking at this guy right here, if you do a U substitution or a substitution, you either let U equal x, which is not really going to help out, I promise, or you let U equal the tangent of x, which again will not help out. Specifically for the U equals tangent of x, if you let U equal that, then you would need a secant squared somewhere in that integrand, or at least you would like a secant squared to be somewhere in that integrand, and there just isn't one there. And this is part of what I tell my students. Think ahead as far as what the ramifications of the techniques that you're going to use will be. So in this case, if I did a U substitution for tangent, without even me writing anything down, I know I'd need a secant squared because that's the derivative of the tangent, and I don't have a secant squared, so I give up on that technique. What else have we learned? Well, besides the U sub, which I'm going to go ahead and X out because that's not going to be very useful, the only other thing that we've actually learned is by parts. And by the way, I should say, every time I say the words by parts, I really mean integration by parts. It's just most of us call it by parts. And because this is a product of a polynomial and a trig function, I feel fairly confident that by parts integration will work here. However, there's a little bit of pre-work to do integration by parts. Let me remind you of something that I tell my students commonly when we go through integration by parts. Now, what you're seeing in red and green on the left-hand side of your screen is actually what I've written down in lecture for my Calc 2 students. And this is within a bigger, different problem than what we're doing right now. But how you choose which piece to integrate and which piece to differentiate is kind of given right here. So when you're handed an integral and you decide I'm going to use integration by parts, you choose one factor within that integrand to integrate, and therefore the rest of the integrand will be the piece that you differentiate. This is the order with which I would make that choice. Look for something to integrate first and make that the biggest possible chunk you can integrate, and then the rest is delegated to being the piece that you're going to differentiate. There is a caveat to this. If it turns out that both factors in the integral can be integrated pretty easily, and that would be something like, oh, if I had an integral of, say, x times the sine of x, I can integrate both of those functions pretty easily, then it's a tie. You then have to switch gears and now look for something you can differentiate, which will eventually change forms. So that's what this is saying right here. If you can integrate both factors, choose U to be the factor whose derivative or derivatives will eventually change form. And if you take a look at this integral right here, for example, I would therefore choose x to be the factor that I would differentiate because its derivative will change forms to become a constant, versus the sine, whose derivative just remains a trig function. And its second derivative will also be a trig function, and so will its 100th derivative. So going back to our problem at hand and thinking about the by parts integration concept, I want to choose something here to integrate. Well, if I take a look at both of these, there's no way I'm going to integrate a tangent squared if it's written like that. So if I did that, I would integrate x. The problem with choosing x to integrate is that it gets worse as you integrate it. It doesn't change to a constant. When you integrate it, it becomes an x squared over 2. Moreover, if you're going to choose to integrate x, that means you're going to differentiate the tangent squared. And the derivative of the tangent squared is not a nice derivative. It's 2 times the tangent times the secant squared. That gets ugly quickly. So little bit of forethought here, just looking at what I'm faced with. If I choose x to integrate and therefore tangent squared to differentiate, things are probably going to get pretty ugly. If faced with an integral like this and you really want to use by parts, well then maybe you should resort to your prerequisite content. Is there something from, let's say, trigonometry that you can take advantage of to rewrite this integrand? And the answer to that is yes. We have a Pythagorean identity. And that identity is that the tangent squared plus 1 is equal to the secant squared. Now, obviously that's not the tangent squared plus 1, so I'll subtract 1 from both sides and arrive at this equivalent statement to the tangent squared. And you may say, well, that doesn't look any better. In fact, it looks worse than the tangent squared. Well, give it a try. Notice in this instance right here that you can distribute the x through that parenthesis. The second term, the negative x dx, that's going to be easy to integrate. That's just going to be an x squared over 2. So really it comes down to, can I integrate this? And you may say, well, that looks just as hard as asking what's the integral of x tangent squared. But it's not hard, actually, because now when I ask, how would I integrate x secant squared, I could go ahead and say, well, let me choose one of these factors to integrate and the other to differentiate. Well, you know that you can actually integrate now both of these factors. You can integrate an x, but you can also integrate a secant squared. Its antiderivative is a tangent. And as my advice said earlier, if you can integrate both factors, then switch gears and choose one of the factors to differentiate. And that one will be the one that will eventually change forms. So if I choose to differentiate x and integrate secant squared of x dx, then all should be good. Now I'm not going to go through the entire by parts integration method because you should know that prior to watching this video, but I will at least write the formula down. The integral of u dv is uv minus the integral of v du. So let's go ahead and off to the side here, I'll do it off to the left, create a table with u and dv. There we have u and dv written down. We're going to differentiate in this direction. So du is going to be simply dx, and we're going to integrate in this direction. And the antiderivative of a secant squared is a tangent of x. Something I want to note before we continue forward. I see it very often that students do not write the dx's here on either the du or the dv. That is incorrect. A differential of a variable, dy, let's just pretend, dy is equal to f prime of x dx. That is by definition. That is, if y is equal to a function of x, then by definition, dy is f prime of x dx. That dx is actually part of dy, just like that dx is part of du here, and the dx is part of dv here. Also, your trig functions have arguments. It's not just a secant squared with nothing. It's secant squared of x, just like its antiderivative is the tangent of x, not tan. That adherence to detail is going to pay off in the long run. All right, so going back to our integral over here, we know that this integral is going to be u times v, which is x tangent of x, minus the integral v du. That's tangent of x dx. And of course, we have this minus integral of x dx on the back end. We know that's minus x squared over 2. Technically, when you run an indefinite integral, there is a constant of integration that pops out here. I'll call it c sub 0. I'm doing that because in reality, the second integral, this guy right here, is going to pop out yet another constant and we'll glue those together. But I'll show you that in action. Rewriting this integral, let's see, we know the antiderivative of the tangent just from our previous work is going to be the natural log absolute value of the secant of x. If you don't know that, write the tangent as sine over cosine and then let u be the cosine and do a u sub. You will get the natural log absolute value of the secant of x. There's a minus sign here because of the minus sign there. So I'm assuming you know that piece of information. Now, when you run that integral, it actually pops out a constant of integration. I'll call that c sub 1. And then we rewrite the rest of it there. Now I'm just going to do one last step. I'm going to combine those two constants into one constant called c. And here's where I'll get students who will ask, do I have to write that step here with the green and the blue ink as two separate constants and then write the final answer with the single constant? And the answer is no. Actually, you could have just held off on writing the constant of integration until the very last step. That's perfectly understandable. You can totally hold off on that and just have gotten down to this right here. And then at the very end said, oh, it was an indefinite integral. Let me go ahead and throw that constant of integration on there. Anyhow, this is the antiderivative of x tangent squared of x, or in other words, the integral of x tangent squared of x dx. As I said, it's just a single example video. I hope this is helpful to you, and I hope you have a wonderful day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.